This is Bojian from CWI Netherlands. Thanks icons invite us to present our current work, Attentive Decision Making and Dynamic Resetting of Continual Running Spiking Recurrent Neural Networks for End-to-End Streaming Keyword Spotting. This work has been done together with Qinghai from Huawei, Cobra, Federico Corradi from TUE, and Bohte from CWI. Neural networks are developing tremendously in recent years, showing their power on image classification, object recognition, and even self-driving. Keyword spotting is one of the key applications in speech recognition. In ordinary cases, the network is trained and tested on well-truncated audio segments. With this setup, the network obtains a fair good performance. Then, the well-trained module will be deployed on the device to accomplish its given task. However, there are two issues that we need to consider in this process. Firstly, the real-world situation differs from experiment setup. In real speech stream, keywords and noise alternate, which means the network needs to locate where is the keywords. Current approach to do that by using voice action detection to locate the audio and a fixed window to make the prediction. Still, this approach relies on pre-processing to obtain segments and a memory buffer to map the sequence into labels. The second problem is that both data and noise in a truncated sample are assigned by a unique label. This inaccurate labeling will cause the model to incorrectly learn some features in the noise instead of the data. For recurrent neural networks, there is one more serious problem. Recurrent neural networks recognize successive information increasingly poorly as the network dynamic became saturated. Here is an example of LSTM. Researchers trained the network on single keywords and tested it on continual input stream. You can see the network performance decaying along with the continual input. So how to solve the problem? For recurrent neural network situation has been sought in periodic reset the internal states of the network, where resetting is typically done by using the empirical measures turned for the task at hand. However, in the real situation, we do not know when to reset the network. To solve the problem, we need to make the network aware of when to make the prediction and when to reset. However, the keyword recognition problem here is no longer a traditional classification problem, but a decision-making problem. For energy-constrained continuous monitoring applications, there is a need for continual running end-to-end spiking neural network solution that minimize the pre- and post-processing and have a minimal memory and processing requirement. Here, we define a specific version of the temporal intensity based on the MFCC representation of the signal, which is also the input of the network. The real-time temporal intensity is then derived from the current mean and associated signal variability and rescale it from 0 to 1 by 10H function. We further define a smoothed version. The smoothed temporal intensity is used to facilitate the process of the evidence accumulation along the speech. In contrast to advanced attention models, our temporal intensity directly localizes the speech pattern ongoing speech sequence. It's parameter-free and can be computed in an online manner. Here we show temporal intensity measurement on two keyword samples and the corresponding MFCC representation. In the sample, we see that both measurements can map close to the envelope of the signal. When we training such a pre-segmented sample, the neural network identically only learns from the data, not from silence or noise. To achieve this, we introduce an instantaneous temporal intensity gated loss function. As the temporal intensity calculates an envelope of the signal, this loss helps the network to learn primarily from the actual signal data, not from the noise. Then, we take the inspiration from the neural module of decision-making based on previous research, and introduce a decision-making circuit with a dynamic reset module of the basal ganglia brain structure. This is specifically involved in decision-making and context-dependent gating. The activity of the action selection system is modeled as a leaky integrator. To pick up the prediction of the network only on the data, we use a gated action value as a conditional prediction probability or confidence to determine when a speech is present. The frame-wise accuracy label for each time step is derived from the gated action with a minimal value, and the whole process is parameter-free. Here is two examples of the action values and the gated version. As the temporal intensity calculates an envelope of the signal, we can see that the gated action value captures the action switch in real data segment very well. Here is the whole decision-making procedure. It's end-to-end. So our spiking recurrent neural networks process the concatenated stream of the data in 3 steps. The first, the temporal intensity measures and MFCC are continued computed in an online manner. For each time step, the smooth temporal intensity and MFCC are fed into the spiking recurrent neural network, resulting in class probability outputs. These outputs are integrated in decision-making action value nodes A and associated gated version bar A. Once a threshold theta is reached, the most activated action is selected and other action values are suppressed. The network moves to the decision collection phase now, which means there is some data part the network recognized. So we define the frame-wise accuracy here to measure the performance on the decision collection period. Once action value for the selected action falls below a set of threshold again, at the end of the tolerance, the label is assigned and we have the final prediction, and the network state is reset. Here is some results of the experiment. We test the network performance on Google speech command V1 and V2. Typically, the V2 dataset is larger than the V1, and we can say that for GSE V1, our network performance is approaching the performance of the current SOTA performance, and on GSE V2, our network outperforms the current state-of-art performance based on the WaveNet spiking neural network. There is one example for the concatenate keywords from GSE V1. We selected 4 correct classified samples from the datasets and turned them into a longer sequence. We feed this longer sequence in the network. The green here means correct classified, and the red means wrong. The arrow here tells the time when to reset the network. So in the sample, we can say that when the network without any resets, it can only classify the first example, and for the rest of the continue inputs are both failed. And for the periodic resets, the network can perform quite good on each example because we applied the reset time at the end of the sequence. And in our dynamic resets, we do not need to tell when to reset, and the network can know it in a decision-making procedure, and the network can have the correct decision when they reset the neural network. We also try something longer, so we add some noise where the label is -1 and big silence. So in this long sequence, we can see our network also perform quite good in these samples. Here is a table for different lengths of sequence. We try the sequence from the 2 concatenated keywords to 128 keywords. For the neural networks without any resets, we can see there is significant accuracy decays with the increase of the sequence length. And when we apply some periodic resets, the network can hold its performance. And when we apply the action selection with dynamic resets, our network outperforms the periodic resets and can hold its performance in a very long sequence. We even do it longer, with 1000 keywords. But for here, we didn't use the frame-wise accuracy to measure the performance. We are using the average editing distance to measure the performance. We can see that our spiking recurrent neural network with dynamic resets only take half of the operations that grew with the periodic resets and the dynamic resets. In addition to that, because we know just V1 and V2, they only have the difference on the environment, so we just training on one dataset and test on another one. So for here, we can see our spiking recurrent neural network with temporal intensity perform well on both datasets and very easy to move to another dataset. So in summary, we can see that our we can see that recurrent neural networks trained in experiment environment still facing some open problems when deployed to the device. In the real situation, the network faces more decision-making problem than classification problem. For instance, where is the data, when to make the prediction, when to reset, and so on. In this work, we show that the compact spiking recurrent neural networks trained on single sample integrate into such extent circuit can then successfully classify sequence of the concurrent keywords. Moreover, they can do this without signal buffering or additional post-processing. We demonstrate an efficient and compact end-to-end event-based solution on that. We also show the dynamic normalization effect by our attention mechanism enable a degree of the environment transfer learning, where the same keywords obtained in the different circumstances are still correctly classified. The principle present here also carry over a similar application of the classical recurrent neural networks, and thus may be of general interest for continual running applications. Thanks for your attention.